Hello everyone, in this video again we are going to define an elliptic curve. In previous video we defined elliptic curve over the real numbers, and here we are going to define elliptic curve over a modulo prime. So modulo a prime, it means elliptic curve over mod p operation. So if we define the normal elliptic curve that was on the real numbers, we can say that E is an elliptic curve. It's a set of x comma y, contains the point x comma y which belongs to set of real numbers r cross r, where y square is equal to x cube plus ax plus b for all a comma b belongs to r, and where 4a cube plus 27b cube b square is not equal to 0, union a point at infinity at theta. So this is known as elliptic curve, and this is known as because 4a cube plus 27b square is not equal to 0. So this is known as non-singular elliptic curve. This is known as non-singular elliptic curve. If we say that 4a or a and b are such that 4a cube plus 27b square is equal to 0, then this elliptic curve will be a singular elliptic curve. Now what we need to do, we need to define elliptic curve point. We need to define this elliptic curve points over ZP, where P is a prime number over ZP, or you can say we need to define elliptic curve over ZP. So if we need to define elliptic curve over ZP, so it means all the operation will be mod P. So this elliptic curve E can be defined as x comma y which belongs to ZP into ZP. So ZP is a group under addition. This we all know that ZP is a group under addition. Now y square is congruent to x cube plus ax plus b mod p, where a comma b belongs to ZP, where a comma b belongs to ZP, and 4a cube plus 27b square is congruent to, not congruent to 0 mod p, and union point at infinity theta. So this curve is this second one, this definition, this curve E is known as non-singular elliptic curve over ZP. This is known as non-singular elliptic curve over ZP. So it means every operation is under mod P and all points are from ZP. All points of this curve are from ZP and every operation is under modulus P. Now let's say we have 2 points on this curve. P is equal to x1 y1. P is equal to x1 y1. This belongs to E, and then we have a Q which is again x2 y2, and this also belongs to this curve E. So either this Q can be minus P, so it means P plus minus P, which is equal to theta. So the one thing is that. Second is if this Q not equal to minus P, then as we define in previous with elliptic curve with reals, then P plus Q is going to be R, and let's say the coordinates of this R are x3 and y3, which belongs to ZP cross ZP. So how we can find x3? x3 is equal to lambda square minus x1 minus x2 mod P. Similarly y3 is equal to lambda x1 minus x3 minus y1 mod P. where we know we have already defined that this lambda is equal to y2 minus y1 into x2 minus x1 inverse if we are talking about mod p operation. Otherwise in the real numbers it was y2 minus y1 upon x2 minus x1. So because it is mod p operation, so y2 minus y1 x2 minus x1 inverse mod p if p is not equal to q, and 3x1 square plus a into 2y1 inverse mod p if p is equal to q, if p is equal to q. So now this E with operation plus is an abelian group whose identity is this theta, the set point at infinity theta. Now the question is, how can we find the points on this elliptic curve mod over ZP? Now if we need to find out the points x3, y3, how can we calculate these points over ZP? So the question is, how we can find points on elliptic curve over ZP. So what we need to do, let's suppose a value for p, let's say p is equal to 11. So when p is equal to 11, then y square is equal to x cube plus ax plus b mod p or mod 11, where x comma y belongs to ZP into ZP. Now what we need to do, we need to find the various values of points x and y. So how can we do that? Let's say this is x, and what is the value of x? All the values in Z11. So it will be like, if we talk about, let's write p here only. So if we talk about p, it will be 0, 1, 2, 3 up to p minus 1. And for this p we need to find y, which is x cube plus ax plus b. So let's say it is y1, y2 up to so on. And then we need to find out that whether it is quadratic residue mod p or not, whether this point is quadratic residue mod p or not. If it is quadratic residue mod p, then this will be the point on curve, otherwise it will not. So the question is, the main thing is how we can find that a particular number is quadratic residue mod p or not. So first let me define again. However, we have already discussed what is quadratic residue mod p. Let me define again what is the residue mod p. So the definition is, let's say x belongs to ZP. Let's say x is a number which belongs to ZP. This is a quadratic modulo p is a quadratic modulo p if and only if. So we write this for if and only if. So if and only if means it is necessary and sufficient condition both. If and only if y square is congruent to x mod p. If and only if y square is congruent to x mod p has a solution. It means y belongs to ZP. So let's take an example. Let's say p is equal to 11. Now p is equal to 11 plus minus 1 whole square is equal to 1. So plus minus 1 whole square 1, it means y square is congruent to x mod p. So this 1 is quadratic residue. Now let's take for 5 plus minus 5 whole square is equal to 3. Under the mod p operation it is equal to 3. So this is also quadratic residue mod p. Plus minus 4 whole square, this we are calculating for mod 11, is equal to 5. So 5 is also quadratic residue mod P. So 1, 3, 5, 9 are quadratic residue mod P. How to check if a number is quadratic residue or not? Like this is just a vague method. If a number is given, how we can check that particular number is quadratic residue or not? This is known as Euler's criteria. We use Euler's criteria. And what Euler's criteria says, given an integer x which belongs to ZP. So this x is quadratic residue mod P. X is quadratic residue mod P if and only if x to the power p minus 1 by 2 is congruent to 1 mod p. If and only if x to the power p minus 1 by 2 is congruent to 1 mod p. Because we are saying about, in the previous example we talk about y square is equal to x, and if y belongs to zp, then what is the y square? X to the power p minus 1 by 2. So this is equal to y to the power p minus 1 is congruent to 1 mod p. Y to the power p minus 1 is congruent to 1 mod p. So if x to the power p minus 1 by 2 is congruent to 1 mod p, then we say that x is quadratic residue mod p. Now how to take under root, how to take square root of this z mod p? Because we need to take a square root also when we want to calculate y. So in this, because we are going to calculate x3 and y3, so if we want to calculate y, we need to take a square root also. So let's take, there is a theorem to calculate square root also, and that theorem says, suppose z is a quadratic residue mod p. Let's say z is equal to quadratic residue mod p. And this p is congruent to 3 mod 4. This is for specific numbers, this is a particular case. This theorem is for particular case, and p is congruent to 3 mod 4. Then 2 square roots of z, then 2 square roots of z mod p are plus minus z to the power p plus 1 by 4 mod p. So this is how to calculate square root. Now we have checked that how to check that whether a number is quadratic residue or not, and then we will check the how to calculate square root. Now let's take an example and calculate the points on elliptic curve under mod p. So let's say p is equal to 11. And y square is equal to x cube plus x plus 6 over z11. So when I write y square is equal to x cube plus x plus 6, it means a is equal to 1 and b is equal to 6, and x belongs to z11. So let me calculate x here. So x will be 0 to 10. Because x belongs to z11. So it will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. This is the value of x. Now here we are going to calculate y, x cube plus x plus 6 mod 11. So when we will calculate, it comes out to be 6, because rest all is 0. Then 6 plus 7 plus 8 mod 11, it will be 8. In this way, now x cube 8 plus 2 plus 6 mod 11. So it is going to be like 10, 16 and it is going to be 5. Similarly, we can calculate all the values of y. So it comes out to be 3, this comes out to be 8, this comes out to be 4, this comes out to be 9, again this is 4, then this is 9, this is 7, and this is 4. So this is x and y. Now we will check whether it is quadratic residue or not. So when we will check that it is quadratic residue or not, how we are going to check it? We are going to check y to the power p minus 1 by 2 is congruent to 1 mod 11. So here p is 11, so y to the power p minus 1, 11 minus 1, 10 by 2, 5 is congruent to 1 mod 11 or not. So this is the value of y. When we will check, it comes out to be this is not, yes this is quadratic residue, yes this is quadratic residue, 4 is not, 5 is yes, 6 is not, 7 is yes, 8 is yes, 9 is not a quadratic residue, and 10 is yes a quadratic residue. So the number which are the quadratic residue, for those numbers we are going to calculate square root or the points. So how to calculate square roots? We have checked it here. Now for example, we want to calculate square root for 2. So it will be z 11 plus 1 to the power 4 mod 11 to the power 4 mod divided by 4. This is divided by 4 mod 11. So z to the power 12 divided by 4, it means 3 mod 11. So when we calculate it for 2, so it will be 2 to the power 3 mod 11. So it comes out to be it is 5. So 5 to the power 3 mod 11, because this y is 5. So it is 5 to the power 3 mod 11, and when we calculate, it comes out to be 4. And because it is plus minus, so the next will be 7. This is like 4 minus 11, which is 7, because, or 11 minus 4, which is 7, because it is inverse. So now here 3, so 3 to the power 3 mod 11, so it comes out to be 5. And when with 5 plus, minus 11 minus 5 is 6. So next one will be 6. For this it will be 4 cube mod 11, and it comes out to be 2 and 9. Again it will be 4 cube mod 11. So same, it will be 2 comma 9. Then it will be 9. So it will be 3 comma 8. For 9 it will be 3 comma 8. And for 4 it will be 2 comma 9. So these are the points, 4 comma 7, 5 comma 6, 2 comma 9. So these are the value of, you can see these are the value of y, like square roots, and then x is this. So this is how we are going to plot the point. So points will be 2 comma 4, 2 comma 7, 3 comma 6, 3 comma 5, 5 comma 9, 5 comma 2, 7 comma 9, 7 comma 2, so 8 comma 8, 8 3, 10 9, and 10 2, and point at infinity also. These are all points belongs to Z 11. So this is how we calculate the points on the curve. So this is 2 comma 4, 2 comma 7, 3 comma 5, 3 comma 6, 4 comma 2, 4 doesn't belong to 5 comma 2, 5 comma 9. So this is how we calculate the points. This we could calculate the square root, just because this 11, because we are initially we check p should be congruent to 3 mod 4, and our p is 11. So this p is 11 is congruent to 3 mod 4. So that's why we took this theorem and we check. So we will always select the prime number like for which we can get that prime p is congruent to 3 mod 4. So this is how we can calculate the points on the elliptic curve. So now we understand what is the meaning of an elliptic curve on real numbers or normal elliptic curve, and then we derive an elliptic curve over modulo prime, and how the operations are performed over this elliptic curve, how we can calculate the points on this elliptic curve. Now in the next video, what we are going to do, we are going to define algorithmic crypto system, a generalized algorithmic crypto system which is based on this elliptic curve. Then the elliptic curve will be then it is known as elliptic curve crypto system. Thank you.